Welcome back to the AI Academy's Ethical Hacking course. In our last lecture, we explored into the TCP/IP model, which is the backbone of modern networking. We explored its layered architecture, each layer's responsibilities, and how it ensures seamless communication across networks. From understanding the role of the application layer in handling data for end-user applications to the Internet layer's critical job of routing packets, we gained a solid foundation in how data flows through networks. Today, we're building on that knowledge to dive into the world of IP addressing and routing. Specifically, in this lecture, we will explore IP addressing fundamentals, including how addresses uniquely identify devices in a network. Routing methods that determine how data packets navigate through interconnected networks to reach their destinations. Subnetting concepts, which help optimize IP address allocation and enhance network efficiency. By the end of this session, you'll have a strong understanding of how devices find and communicate with each other, even across complex networks. Let's get started. Let's start with the introduction to IP addressing. Imagine you're at a party, and the host hands you a unique badge with your name and a number on it. This ensures everyone knows who you are and where to find you if needed. In the world of networking, IP addressing works similarly. It gives every device on a network a unique badge, so they can communicate effectively. Unique identification of hosts using IP addresses. Now, let's talk about those badges I mentioned earlier, IP addresses. These are unique numbers assigned to every device in a network to identify them. Here's how they work. So, how does an IP address look like? An IP addresses typically look like this: 192.168.1.1. This is an example of IPv4 address. Each number in the sequence can range from 0 to 255, separated by dots. In IPv6, the format looks like this: 2000100000000008A2E0370734, allowing for many more unique addresses. Why are IP addresses unique? Just like no two houses on the same street can have the same address, no two devices on the same network can share an IP address. This ensures there's no confusion about where data is headed. How do devices use IP addresses? The source and destination. When you send a message or browse a website, your device includes both its own IP as source and the receiver's IP as destination. Routers and switches, the network's traffic controllers, use these addresses to guide the data to its intended recipient, no matter how many networks it must cross. Dynamic and static IPs. The dynamic IPs, most devices get temporary IPs assigned by a service called DHCP, Dynamic Host Configuration Protocol. Think of it as borrowing a badge when you enter the party. And static IPs, servers or critical devices may have fixed addresses, ensuring they're always reachable. It's like having a permanent badge. In summary, IP addressing and the role of the IP layer are what make the Internet and all networks function seamlessly. Without them, devices couldn't identify or communicate with each other. Data packets wouldn't know where to go, causing chaos. The concept of a globally connected world simply wouldn't exist. So, the next time you browse a website or send an email, remember that there's a lot of complex addressing and routing happening behind the scenes, all thanks to the IP layer and IP addresses. Let us now explore IP packet fragmentation. Imagine you're packing for a trip, and your suitcase is too big to fit in the car trunk. To solve this, you unpack the suitcase into smaller bags that fit easily. Later, when you arrive at your destination, you repack everything into the original suitcase. That's essentially what IP packet fragmentation does for data. So, why we need fragmentation? In computer networks, data is transmitted in small chunks called packets. However, different networks have limits on the size of packets they can handle. This limit is called the maximum transmission unit (MTU). What happens when packets are too big? If a packet is larger than the MTU of a network it needs to travel through, the IP layer breaks it into smaller pieces, or fragments, so it can pass through it. Each fragment is transmitted as an independent IP packet. Why is fragmentation necessary? As different networks may have varying MTU sizes. And it ensures seamless data transfer across heterogeneous networks without losing information. Let us now discuss about types of fragmentation. Fragmentation can be handled in two ways, transparent and non-transparent fragmentation. Here's how they differ. The transparent fragmentation: in this approach, packets are fragmented at an intermediate router but reassembled before being sent to the next network. So, how it works? When a large packet reaches a router that cannot forward it due to MTU limits, the router splits the packet into fragments. These fragments are reassembled into the original packet by another router, called the exit router, before being forwarded to the next network. The key feature is that the subsequent networks are unaware that fragmentation occurred, hence the name, transparent. And the drawback of this method is that it adds extra processing overhead at routers. All fragments must take the same path through the network to be reassembled correctly. It also introduces increased complexity in tracking fragments. And another one is non-transparent fragmentation. In this approach, packets are fragmented, but the fragments are not reassembled until they reach their final destination. So, how it works? When a large packet is fragmented, each fragment is treated as an independent IP packet. The receiving host reassembles the fragments into the original packet. The key feature is that the routers in the path don't reassemble the fragments, which simplifies their processing. And the advantage of non-transparent fragmentation is the reduced processing load on intermediate routers. And it allows fragments to take different paths to the destination. Now we will be discussing about the fragmentation and reassembly process. Here's a step-by-step breakdown of how fragmentation and reassembly work. The fragmentation process includes: Step 1, a large packet exceeds the MTU of a network. Step 2, the IP layer at a router divides the packet into smaller fragments. Step 3, each fragment gets its own IP header, including a fragment offset field to indicate its position in the original packet. Step 4, fragments are transmitted individually. Each fragment travels independently through the network. And some fragments might take different routes to reach the destination. And in the reassembly process. Step 1, the receiving device collects all fragments. In Step 2, it uses the fragment offset and more fragments, MF, flag in the IP header to determine how to reassemble the packet. The fragment offset indicates the fragment's position in the original packet. MF flag indicates if more fragments are coming or if it's the last fragment. And finally, in the Step 3, once all fragments are received and reassembled, the original packet is reconstructed. Challenges in fragmentation and reassembly. While fragmentation allows data to pass through different networks, it introduces some challenges. 1. Increased overhead. Every fragment requires its own IP header, increasing the size of the transmitted data. 2. Loss of fragments. If a single fragment is lost, the entire packet cannot be reassembled. 3. Performance issues. Reassembling packets at the destination can be resource-intensive. Understanding IP packet fragmentation is crucial for network design, ensuring the devices handle fragmentation efficiently. Troubleshooting, identifying issues related to packet loss or excessive fragmentation. Optimizing data transfer, adjusting MTU sizes for specific networks to reduce fragmentation. Let's explore the concept of MTU, maximum transmission unit. The MTU is the largest size of a data packet, including headers, that a network layer protocol can send in a single frame. Think of it like a maximum size for a box you can send through a shipping service. If your item doesn't fit, you'll have to split it into smaller boxes. The MTU ensures that data packets can traverse networks efficiently without exceeding the size limits of any underlying hardware or protocols. It plays a vital role in avoiding unnecessary fragmentation, which can lead to performance issues. Every network has an MTU limit set by the hardware or the network protocol. For example, Ethernet networks commonly use an MTU of 1,500 bytes. Some specialized networks, like MPLS, might use higher MTUs. If a packet exceeds the MTU, it cannot be transmitted in its current size. The packet must either be fragmented or dropped. When a packet exceeds the MTU, the fragmentation, the IP layer splits the packet into smaller fragments, each of which fits within the MTU. These fragments are reassembled at the destination. The Path MTU Discovery, PMTUD. Modern systems try to avoid fragmentation using PMTUD, which detects the smallest MTU along the path and adjusts the packet size accordingly. And the Drop and Notify, if the Don't Fragment (DF) flag is set, the router drops the oversized packet and notifies the sender with an ICMP fragmentation needed message. Let's use an example to see how packets are fragmented. Suppose we are sending a 4,000-byte packet over a network with an MTU of 1,500 bytes. The original packet size is 4,000 bytes. The IP header size is 20 bytes, included in each fragment. Hence the actual data per fragment will be 1,500 bytes, MTU, 20 bytes, header, equals 1,480 bytes. So, the packet will be split into 3 fragments. Fragment 1, data is 1,480 bytes, offset is set to 0, since this is the first fragment which contains the very first chunk of data from the original packet. Since it starts at the beginning, its offset is 0, and the MF flag is set. Next in the fragment 2, the data is 1,480 bytes, the offset is set to 1480 bytes, and the MF flag is set. And while in the last fragment, which is the third, the data is 1,040 bytes, remaining data, offset is 2,960 bytes, and the MF flag is not set, indicates the last fragment. Each fragment is sent as an independent IP packet with its own header. So, why is MTU important? Efficiency. Choosing an appropriate MTU minimizes fragmentation, reducing overhead and improving network performance. Troubleshooting. Understanding MTU helps diagnose issues like packet loss due to dropped fragments or PMTUD failures. Optimization. Adjusting MTU settings can optimize performance for specific applications, such as VPNs or high-speed networks. Let's now discuss about IP address classes, hierarchical addressing. Let's start with IP address classes. In IPv4, IP addresses are divided into 5 classes, A, B, C, D, and E. Each class serves a specific purpose and helps networks organize and allocate addresses. The first one is Class A. The range of Class A starts from 1.0.0.0 to 126.255.255.255. The default subnet mask is 255.0.0.0. Designed for very large networks. The characteristics of class is that it supports approximate 16 million host addresses per network. Used by large organizations and ISPs. For example, a company like Google might use a Class A network. The second class is Class B. The range of Class B starts from 128.0.0.0 to 191.255.255.255. And the default subnet mask is 255.255.0.0. The Class B IP addressing is best suited for the medium-sized networks. It supports approximate 65,000 host addresses per network. Typically used by universities or medium-scale businesses. For example, a university's campus network might use Class B addressing. Next is Class C. the Class C range starts from 192.0.0.0 to 223.255.255.255. The default subnet mask is 255.255.255.0. The Class C is best suited for small networks. The Class C supports up to 254 hosts per network, and is used by small businesses or home networks. For example, your Wi-Fi router at home probably assigns Class C addresses. The Class D, whose range starts from 224.0.0.0 to 239.255.255.255. And it is reserved for multicasting. The Class D IP addresses does not have subnet masks. It is used to send data to multiple devices at once, like streaming video to a group of viewers. The Class E range starts from 240.0.0.0 to 255.255.255.255. It is reserved for experimental purposes. The Class E IP addresses are not assigned for standard use, and is used in research and development. The IP addresses follow a hierarchical structure, which helps manage and route data efficiently. Here's how it works. The two levels are network and host. The network part identifies the network to which a device belongs. For example, in the IP address 192.168.1.1 with subnet mask 255.255.255.0, the 192.168.1 part represents the network. And the host part identifies the specific device within the network. In the same example, the point 1 identifies the device. Why hierarchical addressing is needed? For efficient routing, routers only need to know how to forward packets to the correct network, not every individual host. And the scalability, dividing IP addresses into networks and hosts, allows for efficient use of address space. The IP addresses are written in a dotted decimal format, where each octet, a group of 8 bits, is converted into a decimal number. These decimals are separated by dots. For example, the binary addresses
110000000000000000001
is represented in dotted decimal as 192.168.1.1. This format is easy for humans to read and interpret compared to binary. IP address classes help organize networks by scale and purpose, while hierarchical addressing ensures efficient management. Dotted decimal notation makes IP addresses readable, and TCP versus UDP protocols cater to different communication need of reliable versus fast. Before going to subnetting, let us understand about the basic routing methods. The routing is the process of deciding how data packets travel from a source to a destination across networks. Here are 3 common routing methods. Next-hop routing. In next-hop routing, a router does not maintain a complete path to the destination. Instead, it only knows the next hop address, which is the next router along the path. When a packet arrives at a router, the router checks its routing table. The routing table specifies the next router to forward the packet toward its final destination. The process continues until the packet reaches its destination. The advantages of next-hop routing is that it reduces the size of routing tables since only the next hop is stored. Simplifies the routing decision-making process. The second one is network-specific routing. This method uses the destination network address to make routing decisions. A single entry in the routing table can represent multiple devices on the same network. Instead of specifying a route for each host, the router stores a single route for the entire network. Packets destined for any device within the network are forwarded based on this single route. The advantages of network-specific routing is that it reduces routing table entries. It is efficient for routing in large networks. For example, For a network 192.168.1.0/24, all packets destined for any host in this range, such as 192.168.1.10, 192.168.1.20, use the same next-hop router. And the third one is default routing. The default routing is used when there is no specific route in the routing table for a destination. It's like a fallback route. A default route points to a catch-all path, typically toward an ISP or upstream router. If the destination network is not explicitly listed in the routing table, the packet is sent to the default route. The advantages of default routing is that it is useful for smaller networks or routers with limited routing knowledge. It simplifies routing in stub networks, networks with a single connection to the Internet. Example: a default route pointing to 10.0.0.1 might look like destination 0.0.0.0 next hop 10.0.0.0.1. Here, 0.0.0.0.0 represents all destinations that are not covered by more specific routes. Let's now explore subnets and their importance in networking. Introduction to subnets. A subnet, short for subnetwork, is a smaller network taken out of a larger network. It helps divide an IP network into manageable segments, optimizing performance and enhancing security. Subnetting plays a crucial role in efficiently utilizing the IP address space. Subnets as subsets of Class A, B, or C networks. Each IP address class, A, B, or C, has a predefined range and capacity for devices. Subnetting allows us to split these large networks into smaller, logical networks. So, why we subnets? 1. Efficient addressing, to avoid wasting IP addresses. For example, if you only need 50 devices, you don't have to use an entire Class B network that supports thousands. 2. Improved security, by isolating parts of the network, you limit access and potential damage in case of a breach. 3. Better performance, reduces network congestion by limiting broadcast domains, areas where devices hear each other's broadcast messages. The Class A IP address range starts from 1.0.0.0 to 126.0.0.0. And it supports over 16 million hosts, but subnetting can create smaller networks within this massive range. Whereas the Class B IP address range starts from 128.0.0.0 to 191.255.0.0. Default supports up to approximate 65,000 hosts. Subnetting allows splitting this into smaller networks. And the Class C IP address range starts from 192.0.0.0 to 223.255.255.0. Default supports 254 hosts, but subnetting can create even smaller segments for specific use cases. For example, a Class C network 192.168.1.0/24, default subnet mask 255.255.255.0, can be split into two subnets. O subnet 1, 192.168.1.0/25, 128 addresses. O subnet 2, 192.168.1.128/25, 128 addresses. Network masks and their role in hierarchical addressing. The subnet mask is a critical tool in defining subnets. It determines which part of an IP address belongs to the network and which part identifies a specific device or host. So, what is a subnet mask? The subnet mask is a 32-bit number used in conjunction with an IP address. It masks the network portion of the IP address, leaving the host portion for individual devices. Represented in the same dotted decimal format as IP addresses, such as 255.255.255.0. How subnet masks work. The mask divides the 32 bits of an IP address into two parts. Network part specifies the network, such as 192.168.1.0. Host part identifies devices within that network, such as 192.168.1.1. For example, for an IP address 192.168.1.10 with a subnet mask 255.255.255.0. The network part is 192.168.1 and the host part is 10. Let's discuss about CIDR notation. Instead of writing the full subnet mask, we often use CIDR, classless interdomain routing, notation. It represents the number of bits used for the network part. For example, /24 means the first 24 bits are for the network, which is equivalent to 255.255.255.0. Subnet masks are essential for hierarchical addressing because 1. Define subnets, allow dividing a large network into smaller, more manageable ones. 2. Enable routing, help routers determine whether an IP address belongs to a specific subnet or needs to be forwarded elsewhere. 3. Optimize address use, ensure no address space is wasted. Example of subnetting a Class B network. The default Class B network is 172.16.0.0/16, support 65,536 hosts. Breaking the subnet into smaller networks using /24. Subnet 1, 172.16.0.0/24, 256 hosts. Subnet 2, 172.16.1.0/24, 256 hosts. Subnet 3, 172.16.2.0/24, 256 hosts. Why is subnetting important? Scalability allows networks to grow in a structured way. Security isolates sensitive parts of the network. Performance reduces congestion by limiting broadcast traffic. Cost efficiency optimize IP address allocation. Understanding VLSM and CIDR. Let's dive into how VLSM, variable length subnet masking, and CIDR, classless interdomain routing, help create efficient networks and optimize IP address usage. We'll also walk through practical subnetting steps, including calculations and verification. What is VLSM? VLSM allows creating subnets of different sizes from a single network. Instead of splitting a network into subnets of equal sizes, like traditional subnetting, VLSM lets you allocate IP addresses based on specific needs. How does VLSM work? Start with a large network and divide it into subnets. Assign smaller subnet masks to networks with fewer hosts and larger masks to those needing more hosts. Efficiently utilize the available address space by avoiding wasted addresses. For example, imagine a company with these requirements. Subnet 150 hosts, needs at least 64 IPs. Subnet 225 hosts, needs at least 32 IPs. Subnet 310 hosts, needs at least 16 IPs. Start with a Class C network, 192.168.1.0/24, 256 addresses. Subnet 1, 192.168.1.0/26, 64 addresses from 192.168.1.0 to 192.168.1.63. Subnet 2, 192.168.1.64/27, 32 addresses from 192.168.1.64 to 192.168.1.95. Subnet 3, 192.168.1.96/28, 16 addresses from 192.168.1.96 to 192.168.1.111. This approach minimizes wastage of addresses while meeting requirements. In summary, VLSM, divide a large network into subnets of varying sizes to minimize waste. CIDR, use prefix notation to flexibly allocate and aggregate IP addresses. Subnetting, calculate masks and assign address ranges to meet specific needs, then verify using tools like ping and routing tables. With this we will end out today's lecture. Thank you for joining today's session. In this lecture, we explored the foundational concepts of IPv4 addressing and subnetting. We learned how IP addresses uniquely identify devices on a network and examined different routing methods that enable data to travel efficiently. We also touched upon subnetting, which helps manage and optimize IP address allocation for networks of varying sizes. In our next lecture, we'll dive into IPv6 in detail. If you found today's lecture insightful, please like, share, and subscribe to stay updated with more engaging content on ethical hacking and networking. Your support helps us grow and bring you even better material. See you in the next lecture.